Hi, I'm Babak Anosari at Drexel University, and I'm currently working on synthesis, characterization, and applications of 2D materials MXene. MXenes are two-dimensional transition metal carbides and nitrides that were discovered in 2011 at Drexel University. In this study, we present a new level of atomic ordering in 2D materials by introducing two new families of ordered MXenes. In less than 3 years, more than a dozen different MXenes have been experimentally synthesized. MXene synthesis is a top-down method which starts with the family of ternary carbides called MAX phases, discovered at Drexel in 1996. M in MAX represents early transition metals, red circles here, A represents A group elements, blue circles here, and X is either carbon or nitrogen, black circles. There are more than 70 different MAX phases known to date that are basically layers of transition metal carbides separated with A-element layers, such as aluminum. By putting MAX phases in an acid, such as hydrofluoric acid, the A element in MAX is selectively etched and only carbide layers remain. By further processing, 2D MXene flakes can be separated. These materials display many interesting properties, particularly for energy storage, both for battery and supercapacitor electrodes. In 2014 and 2015, a set of new MAX phases were discovered, in which two different transition metals are occupying the M sides in a layered format, such as molybdenum-2 titanium aluminum carbon 2 and chromium-2 titanium aluminum carbon 2, which opened a new door to synthesize ordered MXenes. By etching these new ordered MAX phases, we have been able to make new MXenes that were not experimentally possible to make before.
Hi, and I am Yuxie from Oak Ridge National Laboratory. I'm working on the theoretical prediction and characterization of MXenes. As Babak introduced, the ordered double transition metal MAX phases will lead to the new ordered double transition metal MXenes. But it is important to understand whether the ordered structure is metastable state or ground state. From density functional theory simulations, we indeed found that the ordered structure is the ground state for most of the so-called 212 MXenes and for all of the 223 MXenes. Our calculations predict that these are large families of materials. Moreover, the calculated density of states of MO2 TiC2 MXenes with hydroxyl, oxygen, and fluorine terminations are quite similar to that of MO3C2 MXenes, but very different from Ti3C2 MXenes. This suggests that the electronic properties of the fully ordered double transition metal MXenes will be mainly controlled by the outer transition metal, with a small influence from the inner transition metal. Our findings not only expand the diversity of the two-dimensional nanomaterials, but also show that the new MXenes are a way of accessing new properties distinct from those of previously synthesized single metal MXenes.
By experimentally synthesizing Moly2 TiC2, Moly2 Ti2C3, and chromium-2 TiC2, we validated our DFT predictions. Electrochemical results also showed that MO2 TiC2 behaves differently from its monoatomic counterpart Ti3C2 MXene. We believe this is a major discovery because it opens new horizons in the 2D materials field. We can now design new structures and control properties by varying elements in carbides containing 3 or 4 layers of transition metal atoms, and further modify their properties by changing the surface terminations. This should lead to unique combinations of properties such as metallic conductivity combined with surface hydrophilicity, and will unquestionably render MXene the largest family of known 2D materials.